Hi, hello friends. Welcome to T Academy. Now I would like to discuss the power system important points. In this video, we will discuss more than 100 plus important points or formulas regarding the power system subject of electrical and electronics engineering and electrical instrumentation engineering. Right now, the first point we will talk about the power system transmission lines. Okay, so first point here we'll talk about here it is uh, if PR is the receiving end power, then Vs is the sending end voltage, Vr is the receiving end voltage divided by XL is a transmission line reactance into sin delta, where delta is nothing but it's a load angle. Okay. Now, by keeping the high value of sending end voltage, what is the advantages? The line losses and the area and volume of the conductor is reduced here. Line losses means the power losses is proportional to 1 by V square into cos square phi. We can say power losses is inversely proportional to voltage, sending end voltage. Higher the voltage, lesser will be the losses. Higher the power factor, lesser will be the losses here. That's the point here. So by increasing the more voltage, the losses can be minimized and the area also minimized here. So for high power transfer XL should be lower value. So this formula is here, no? So in that formula here we have a XL here. What is the XL is nothing but transmission line reactance. So the transmission line reactance can be reduced by using what? First, parallel lines. Okay, if you are using two parallel transmission lines, the net reactance will be reduced here. And series capacitance means we add one more capacitor here in series with the reactance, so that the net reactance effect will be reduced here. And by using the bundle conductors, so bundle conductors means we can where virtually we are increasing the radius of the conductor. As the R increases, automatically L decreases, so XL decreases. Okay, we'll discuss this point in the next coming important formulas. Right now, here another point here. Resistor dissipates the real power, whereas L and C, inductor and capacitor, stores a reactive power here. Okay, so here there is a reactive power condition is given. What is that? If QR is equal to Q demand is equal to Q supplied, that is reactive power supply is equal to, that means by applying some extra components here, such as shunt capacitor, series capacitor. Okay, so demand means what is load is asking and what is supply is supplying. Okay, if these two are equal means QR will be automatically 0. Okay, now but 90% of the major cases the demand will be higher compared to supply, because 90% of the industrial loads are nothing but our induction machines only. Now if VR is less than Vs, receiving end voltage is less than is Vs means generally this demand is more compared to supply. But when receiving end voltage is greater than sending end voltage, you remember this formula here, it's called as a Ferranti effect. Okay, because of the capacitive nature of this transmission line, at no load condition, or we can say lightly loaded condition, the Ferranti effect is more. Because because of capacitance effect, the receiving end voltage is higher compared to sending end voltage. Okay, that means the capacitor is delivering the reactive power to the system. Okay, now what is the reactive power receiving end here? QR is equal to Vs Vr by XL into cos delta 1 minus delta 2. Okay, minus Vr all square divided by XL. So here Vs Vr XL, delta 1 and delta 2 are the sending end and receiving end load angles of the transmission line. Okay, now next point, important formula. With higher power factor, as we discussed, with the higher power factor, whatever the power losses decreases. Power losses decreases means whatever the power supplied by the system reduces. So if the power supplied by the system reduces, automatically generator capacity also reduces. So generator capacity is reduced here. The rating of the generator, or we can say it is a capacity of the generator is reduced. So reactive power burden on the generator is reduced. Okay, automatically current decreases, power loss will decrease. So same point we discussed earlier. Next point, in the power system, in case of star load, P three phase is equal to root 3 into VL into IL into cos phi. So most of the students will confuse here. Okay, now this general formula, this is common for star and delta, which can also be written as VL square divided by Z into cos phi. So VL is nothing but line voltage here. Okay, so Q three phase is equal to VL square divided by Z into sin phi. Okay, remember here three phase here. Okay, and similarly for delta connected load, P3 phase is equal to 3 times that of VL square divided by Z into cos square. Why it is, sir? Because here line voltage is nothing but phase voltage. There is one more comparison here. For the same level of voltage, rating voltage, the P3 phase of delta is equal to P3 phase of star into 3. That means the delta winding will carry more amount of power compared to star connected winding for same level of voltages. Okay. Now next one. By using shunt capacitor, the power factor is improved. The voltage regulation, that means changing from no load to full load voltage, can be reduced and the power system stability can be increased here. Okay. So QC means the compensation we are supplying here is equal to Pi into tan phi 1 minus tan phi 2. So input power can be written as, if the problem is given only output here, output in efficiency is specified, not input power. So P naught by eta we can take. Now the reactive power QCPH, so QCPH is equal to 2 pi F into CPH into VP square. How we got this formula here? So QCPH is nothing but VPH square divided by XC. So from this we can easily remember this formula. Now capacitance per phase, CPH is equal to P1 into tan pi 1 minus tan pi 2. So we already studied here, it is nothing but QC line and divide by 3 because it's a phase, okay, into 2 pi F into VPH square here. Okay, so we'll move to the next page. Now for a star connected capacitor bank where we have that capacitor of each cell is going to be, so capacitor, for example, if we take a star network here like this, we'll take the capacitance in one phase. So similarly we have another phase capacitance like this. Okay, now what about this capacitance of each cell? So suppose if we take this entire capacitance CPH, capacitance is a CS here. So CS is the capacitance of each cell is equal to N into CPH. Why? Because remember here, these capacitance are considered in series here. So overall capacitance will be lesser compared to CS. Okay. Now, next point. By using shunt reactor, the component shunt reactor component shunt reactor, what will happen is generally we will use this shunt reactor especially in case of Ferranti effect. Remember Ferranti effect. So why, sir? So Ferranti effect causes what? Receiving end voltage is higher compared to sending end voltage. At that time, the capacitor will deliver the reactive power. To control the reactive power, we add one more element such as shunt reactor, which will absorb the extra reactive power. Okay, so that it will increase the voltage regulation. Generally, it will change the voltage regulation from negative to positive. Remember here. Okay, when the Ferranti effect comes, the voltage regulation will become negative. Okay, so it will changes the negative to positive and power factor from lead to lagging. Okay, general condition is leading, but what we will do, we'll add shunt reactor to reduce it to shunt reactor to reduce it to lagging power factor. Okay, and stability will decrease. Okay, right. So now QL, the how much reactive power supplied by inductor, so is equal to Pi into tan phi 2 minus tan. Earlier it was a tan phi 1 minus phi 2 in case of shunt capacitor. Now here it is tan phi 2 minus tan phi 1. Okay, similarly we can find the inductance per phase. L phase is equal to Vps divided by QL phase into 2pf or 2 pi f. So QL per phase is equal to QL by 3. So generally it is nothing but it is for 3 phase. QL is nothing but 3 phase. 3 phase is equal to 3 times that of Q line per phase. Okay, now one more point here, one important point. But for anti effect we have, so receiving in voltage, we know that receiving in voltage is greater than that of sending in voltage, but receiving in voltage is higher than sending in voltage by the amount of what? Vs into omega square into LC. So this is the amount extra voltage will be produced. This is because of capacitive in nature. Okay, this delta Vs, delta Vr can be written as, so 4 V square means 2 pi f, 4 pi f square Vs into L square divided by V square. Okay, and also write as a Vs into omega square into LC. So both are same only. Now at no load, receiving end voltage is, it can be written as a formula as Vs by A. So by considering the ABCD parameters of the transmission line, and the Is is equal to sending end current is equal to charging current is equal to C into Vs by A. So C into Vs by A. Okay. Now with LSH shunt reactor, what we can, how much of reactance means XH is equal to VR by IR, which is nothing but in terms of ABCD parameters is the important formula, especially if you are preparing for any competitive exams like Transco AE exams. So this formula will be important. You should keep in mind. Okay, so B divided by 1 minus A. Now next point. Shunt capacitor use it up to 132 kV, 132 kV, and shunt reactor from 400 to 765 kV. Why? Because in high voltage transmission lines only voltage booster will be there because of Ferranti effect. Okay, in normal low voltage lines it will not be there. So by using the series capacitance, we can improve the stability. Why? Because P is equal to EV by X into sin delta. We can reduce the XL there. Okay, so by using capacitor, so P is equal to right, EV by, so P is equal to EV by X here. We can reduce this X by adding a capacitance so that XL minus XC will occur. Okay, CSE stability can also be improved. Power transfer capability will increase. Voltage regulation will decrease. Voltage regulation means change in the voltage. Change in the voltage here. Next one, there is one more device is there which can perform the operations of both inductor as well as capacitor. That means it can supply leading reactive power. It can also draw the leading reactive power. Okay, the synchronous phase modifier is nothing but a synchronous motor. Okay, which can act as a reactor, which can act as a capacitor. Okay, which can act as a reactor when under excited, capacitor when it is over excited. Now here the formula is QC is equal to P1 into tan phi 1 minus P1 plus P2 into tan phi 2. Sir, why it is, sir, we are considering here P1 plus PS here? Generally, it is a synchronous phase modifier, means it is just like a synchronous motor, so which will draw some extra amount of power, yes sir, for its no load operation condition. So this extra amount of power which you are supplying for no load rotation of the generator, no load rotation. Why? Because a synchronous machine is a machine which runs at a speed of synchronous speed only, so for which it requires some extra amount of energy to compensate its rotational losses. Okay, now here suppose if it acts as an inductor, okay, when it is under excited, it will, here the formula is P1 plus PS into tan phi 2 minus P1 into tan. Here we get a voltage formula, right? And power factor is equal to cos inversion of tan cos of tan inversion of QL by PS here, right? So over shunt compensator, synchronous phase modifier has disadvantages. Okay, so costly uh, and consume active power and power also. So it will have a drawback. Okay, that's why we are not using mostly case. Why? Because for example, in a one substation, if you are having, if you want to supply the reactive power by using SPM, synchronous phase modifier, for which it will take some, for example, it will take 110 watts of, not 10 watts, it will take 10 megawatts of energy. I'm just giving example, 10 megawatts of energy to consuming for rotational losses, for example. Suppose if you want to have 5 substation, if you want to provide 5 substation with the synchronous phase modifier, so it will have to provide 50 megawatts of power. Okay, so the cost will be increased because cost increase because we need to install this synchronous phase modifiers or synchronous motors. Along with its, we need to supply extra energy to maintain its synchronism. So that also makes it more costlier. So which is practically not possible to implement. Next case here. At substations, shunt compensators are used instead of SPM, which is very which is used only in factories. Okay, used by factories. If transmission line TR and TS turns on the receiving and sending end side of the online tap changing transformer. So TR and TS is the tap changing ratios here, which is equal to 1 for off nominal settings. Okay, why we are doing this? Because in order to control the voltage, so voltage control, we can use on load tap changing transformers. Okay, on load tap changing transformers we can use here. Now there is another one, booster transformer, which can be used to obtain the uniform voltage along the transmission line. So this is especially used in trains, locomotives. We can call it a traction system. Okay, it is a transmission, right? Next one, the PR. So PR is equal to VS VR by B into cos beta minus delta. So B is nothing but its inductance is having a value of beta, is a transmission line reactance angle beta, and angle between the VS sending end voltage receiving voltage is delta here, minus AVR square by B into cos beta minus delta. So QR, similarly here we have a constant, here we have a sine term. That's it. So sending end powers PS and QS. So PS is just reciprocal of this one here. So here we have A, here it becomes D, VR square becomes VS square by B into cos of beta minus alpha minus of VS VR by B into cos of beta plus delta. Here we have minus sign, just remember here minus and here we have a plus sign here. Just focus on these formulas. Okay. Now, for maximum receiving end power can be obtained when the delta is equal to beta. What is the delta? Delta is nothing but load angle. Beta is nothing but impedance angle. Okay, and QR is equal to minus QL here. Okay, minus negative here. Sorry, negative sign at beta equal delta. So that what is the meaning of this beta equal delta here? As we discussed earlier, that beta is nothing but load angle which is equal to impedance angle. At this condition, the QR receiving end power should be negative. That means that leading VRs has to be supplied to the load here. Okay, the QR will be negative. Now next one, for short transmission line with a B is equal to XL and A is equal to D is equal to 1, C is equal to 0 is neglected here. So this is also important point in examination point of view. We have PS is equal to PR is equal to VS VR by XL into sin delta. So we generally made a short formula here, and PR is proportional to sin into delta. Okay, when QR when delta is small and not given, so then we can say QR is equal to VR by XL into Vs minus VR. So generally the receiving end reactive power is proportional to difference between the voltage here, or you can say voltage drop. Okay, now what is the Q average value? So Q average value is nothing but receiving end reactive power plus sending end reactive power divided by 2, which can be written as Vs square minus VR square by 2XL. And remember here, we are supplying the reactive power to compensate the voltage, I mean to compensate the voltage drop and to make the sending end voltage equal to receiving end voltage. Okay, so if it that true, then average power will be average reactive power will be 0. Okay, and this formula is valid when Vs is not equal to Vr. Understand this point. So this formula is valid at this condition. Now, positive sequence group replacement actual impedance or reactive power circuit. We'll see this next when we are discussing about the fault analysis. In case of ACSR, okay, all conductors steel reinforced, aluminum conductors steel reinforced here. Sorry, N is equal to layer, N is the number of layer number, and D is the diameter of the each strand. Total number of strands in the group of conductor is 3n square minus 3n plus 1, and overall diameter of the strand is equal to 2n minus 1 into D, where D is the small d is the diameter of each strand here. Okay, and in next here L internal flux linkages due to ACSR conductor is equal to mu r by 2 into 10 power minus 7 into 10 power minus 7, sorry. If mu r is equal to 1 means relative permeability of air is nothing but 1 generally. Okay, relative permeability of air is equal to 1, and then internal inductance is equal to 0.05 into millihenries per kilometer. External inductance is equal to 2 into 10 power minus 7 ln of d by r is equal to 0.2 into ln of d by r millihenry per kilometer. Then total inductance L is equal to, so 2 into 10 power minus 7 into ln of d by r dash actually. Why? Because inductance, when you are adding these two formulas, so this will become r dash. So what is this r dash here is nothing but 0.7788 times that of r here. So in case of halo conductors means it's a conductor which won't have any internal flux linkages. So internally halo, so everything, nothing is here. So at that time internal flux linkage is 0. So at that time the total inductance is equal to, so 2 into 10 power minus 7 into ln of d by r, so which is same formula as that of external inductance. Next, transposing of lines is done to reduce a distortion either in communication or power lines. Okay, the voltage which produces a disturbance in the telecommunication lines is nothing but Vc is equal to disturbances 2 into mu naught into F into Ia into ln of d2 by d1 here. So generally inductance multiplied with the current here. In case of unsymmetrical line to line LG and a line to line ground faults, so these are nothing but unsymmetrical fault, we have to transpose the telecommunication lines, telecommunication. Why? Because if it not there means the inductance will be unequal, so that the losses in the voltage drop will be more, and it will cause interference with the communication lines. Next one, in a three-phase system, due to electromagnetic effect, the three-phase currents IR, IY, IB is not equal to 0, and similarly because of electrostatic effect, VR plus VY plus VB is not equal to 0. So this is practically okay, theoretically we can say it's 0, but practically it is not 0. So in three-phase system we have that L phase is equal to LR is equal to LY is equal to LV. That what is the meaning here? They all are phase quantities. Is equal to 2 into 10 power minus 7 into ln of d1 d2 d3 divided by ra dash into rb dash into rc dash. What is this DNEB? It is nothing but geometrical mean distance divided by geometrical mean radius here. Okay, so in case of bundle conductors, we have L is equal to uh, L is equal to 2 into 10 power minus 7 into ln of dm by ds. Okay, in double circuit line we have L is equal to, or L R is equal to 2 into 10 power minus 7 into ln of dm r1 into dm r2 into dm r3, where dm is about geometrical mean radius, geometrical mean distance, sorry, divided by geometrical mean radius. Okay, and we'll see next session of this formulas here. Thank you friends, thanks for watching my video. If you like my video, please subscribe, share and comment. Okay, so we'll continue in the next upcoming short notes of power system. Thank you, have a nice day.